Okay, good afternoon, everybody. Hope everyone's having a wonderful day. So today I'm going to be wrapping up first a little bit about properties of regular languages, and then we'll be easing into a topic that I do consider a little bit more challenging in this class, but at the same time, it's also one that I would consider it can blow your mind a little bit. Like, there are things in this class that are just like a little strange at first. That it's like, okay, that kind of makes sense. But you really have to play around with the ideas a little bit more to get really cozy with it. So before we get to that, I just want to remind people where we were last day. So last day I was talking a bit about algebraic laws, regular expressions. Then I started talking about properties of regular languages. So another one of these kind of typical decision-based problems, this is the one actually I gave you towards the beginning of this class, is if I give you some string W, is W in the language? So if I give you some regular language, the question is, how do you do it? Now, with a regular language, it's nice and easy. So just as a reminder, remember, I'm talking about a language as a description of it, not literally the language itself. Obviously, if I give you the whole language, you can check if it's member in it or not. However, usually we're interested in infinite languages, so ones that aren't of a finite length in number of members. Because remember last day I told you that, oh yeah, any finite language is regular. Remember I told you that you could basically build any kind of regular expression for those kind of things. But my thing here is that I want to know if W is in the language or not in the language. So I'm going to be describing it in terms of how do you do this with a finite automaton and then a regular expression. So I must also note that these aren't necessarily the fastest ways of doing this. It is just one way of doing it. But this one I would consider pretty much like this is a bing bang awesome way of doing it. This is a very good way of approaching this. And this is very natural for what we've done up to this point. So if you're given W, all you have to do is you just think about it. If you have a finite automaton, you just simulate it, right? Remember, that's what we've done all up to this point. I just give you W and you read off the symbols from left to right. Now, the great thing about this is that if the automaton ends in a final state, then you can say, yes, it is in the language, right? If it doesn't, meaning it's a non-final state, that means the machine isn't accepting. So you say the answer is no. Now, a nice simple way of implementing this, and this is one that you can do, it's a very fast algorithm, and I'd like to try to show you those different ways of representing the finite state automaton, because when I do this, very often you imagine it like either the diagram or the table. Well, if you think about more like the table, you can think of it like a two-dimensional array, a lookup table of sorts. And what you do is imagine if I gave you a string W and its length was, say, n. So what I can do is I could take my representation of, say, for example, a DFA. It doesn't necessarily have to be a DFA, but in our case, it's a DFA. But what I could do is I could take this and I could just go on each one of the transitions. Now, in a DFA specifically, it takes constant time. And the other ones, it might not. It might not. As you remember, there are states. Like an NFA has a set of states. So you would have to essentially exhaust these, which is time consuming. But in a DFA, it's really nice and fast. So I could just simply look up in the table where I need to go for the next state. And I can look in each one of the successive entries in my two-dimensional lookup table. And then I could just do this, and since the length of the the length of the string is n, this will take linear time where n is the length of the string. So this is very fast. Like this is like if you, this is why often people want to have things like DFAs. It's because DFAs are very simple to represent, and also there's very nice algorithms for doing things with DFAs. So this is a very nice algorithm. I just feel like mentioning that. It's a very nice algorithm. So if you're doing things with like if you can convert this what you're describing into a DFA, there's a lot of these different algorithms you have. For example, when I test emptiness, like last day, with a DFA I can use that reachability approach where I find a path. As long as I can find at least one path, I can do that with a DFA, and I also can do this with a DFA, right? It's nice and simple. With a regular expression, convert it to a finite automaton and then do this. That's what I would recommend doing if you just want one algorithm that can do this. But there's, like I said, there's many ways you could do these things. This is the most classic way of doing it, is if you get into a finite automaton state like this representation, just process it, just like you would think with a DFA. Is that clear, everybody? So all I'm saying is what we've basically been doing up to this point, right? I give you some string, I process it, and I use the extended transition function to process it. But in an actual computer implementation, you just have like a two-dimensional array. You do each transition successfully, and you'd maintain a state as you go through this, and then you get to the end, and it's either accepting or not accepting. Now, the one that I want to point out, and this is why I say that this isn't necessarily the most efficient way of doing it, this approach I'm going to describe next for this other decision-based problem is in fact non-constructive, the way I'm going to describe it to you. There is a way to make it constructive, but so let me just be clear about what I'm going to do next. So what I would like to do is I would like to know, if I gave you two regular languages, whether the two languages are in fact equal to one another. So of course, if they're finite languages, this wouldn't be too bad. I could actually just check them directly, because there's a finite number of elements. I could just check if they're the case. However, typically the ones we're interested in have there's an infinite number of them, right? So I need some way to know how I can test if they're equal or not. So here's a neat theorem. And you can cook this up into something that you could use to test for equality between two regular languages. So given two regular languages, L1 and L2, there exists an algorithm to determine if L1 is equal to L2. So this is my little theorem here. And this is surprisingly simple to prove, and it's kind of, in that way, it's kind of nice. So here's the trick. Here's the trick. Now remember last day I talked all about those closure properties that regular languages have. So remember that if I have like union, intersection, complement, set, difference, all of them are closed under regular operations on regular languages. So I have my operators, I got all these other things, like even reversal. All of them are closed. So if I have a regular language, I apply one of these, or if I have a pair of them, I apply this, it still stays regular. So I'm going to carefully craft a language that's going to remain regular. And if I do it in this specific way, if I craft it the right way, I can actually ensure it is regular, and that means that there exists a DFA for it. So that's just because the definition says that, hey, look, if it's a regular language, then there exists a DFA that recognizes it, right? So here's the trick. So what I'm going to do is I'm going to take the two languages. I'm going to have L1 and the complement of L2, I'm going to take the intersection of this, and then I'm going to union this with, essentially it's reverse here. I'm going to take the complement of L1 and I'm going to intersect it with L2. So because union is closed, intersection is closed, and complement are all closed, you could build conceivably this into L3, and L3 is in fact, as a result, regular. So that means that there exists the DFA that recognizes L3. Now you ask the question, okay, well, what do you do with L3? Well, there's a DFA now. And what you could do is you can test for if L3 is empty. So I talked about this last day. So remember, that's where you use that reachability process where I just do a graph traversal algorithm. I just find if there exists one path. So I just use this process on the DFA for L3. So the reason why I say this is non-constructive is that I haven't described to you how I could take the DFAs for L1 and L2 to form L3. There are ways to do this, but I just for the sake of time, I do not have time to talk about those details here. But just be aware it does actually exist a way to do this. So the main connection I want you to know about is that if L3 is empty, then L1 is equal to L2. If you look closely at how I constructed L3, this actually represents something else. And once you see it, it spits out quite quickly if you remember how set equality works. So you can prove both directions of this part right here as follows. So if I assume L3 is empty, then it must be that both, no, so I take the first part here, L1 intersect L2 bar. Now, this actually can be rewritten in terms of set difference. It says that L1 set minus L2 bar. Actually, sorry, no. It's just L1 set minus L2. I was getting a little ahead of myself. So this is actually equal to this. This is just a relationship intersection has with set difference. And if you know that L3 is empty, this implies that if I take everything that's in L1 and I do set minus on L2, and I know L3 is in fact empty, then you can notice that the result has to be empty here. Why? Because remember, I take this and I take the results of both of these and I do the union on them, right? So it means that this one might be empty. That one might be empty, but they notice that if I have L3, I need to make sure it's all empty, right? Because this is just a union here. But either way, because of the properties of set difference, this actually implies that L1 is a subset of L2. So if you're not sure about this, take out draw a Venn diagram out, take L1 and L2 based on the information I just described here and try to see which one gets contained in the other. If you're not convinced, try a simple, just a basic set and try doing it like this. And under this assumption, you'll see that actually implies that one is a subset of the other. Now, if you take the other case here, so right here, if I just do the same thing to the other side, you'll notice that this has the exact same result. But that implies that L2 is a subset of L1. So L2 is a subset of L1. And if you remember your set theory, if there's subset relations on both directions, they go both ways, that means that it is in fact that L1 is equal to L2. Now, over here, so this is the other direction. So if I assume that L1 is equal to L2, I would like to show that in fact L3 is going to yield empty. So if you think about this, if I have L1 intersect L2 and L2 bar, sorry, but L2 is equal to L1, that's L1 intersect L1 bar. Now, what's L1 bar? That's the complement of L1. So that means, of course, that we're talking about, what are we talking about? Well, we're talking about you take everything, and then you take everything it isn't, and you try to intersect the two. Are there any common elements between the two, everybody? Yes or no? Are there any common elements between, if I write L1 intersect L1 bar, are there any elements that are in common between these two sets? No, right? Very good. So that means that the result will be empty set, and this applies on both of these. I take the union of both, and I end up with the empty set. So this is, it's actually kind of cute how this all works out. So if you have this relationship set up, you could just use testing emptiness to determine if two languages are equal to one another. So you can use this as a cookbook. Say if you have, say you have L1 and L2, they may have their own DFAs. If you know ways you can combine the DFAs using these regular operators, then you can conceivably create L3, and then you can check if it's empty or not. It's kind of neat. So that's a non-constructive proof I've given you. So I encourage you, if you feel like exploring a little bit more, there do exist ways to build automata out of these regular operators. Now, one other thing I do want to remark, because I did say that this isn't necessarily the fastest way, or at least the most utility-based way of doing this. I want to make one remark. I was hoping I was going to have more time this term to talk about this, but just because this course is much more broader than just the context of automata, I want to talk briefly about minimization of DFAs. Just briefly. But I want to point out that there exists algorithms. There do exist algorithms. For minimizing a DFA so that it has the smallest possible number of states. smallest possible number of states. Now, you might ask, Dan, why would this be useful for checking if they're two languages equal? Well, the idea is that if you can minimize a DFA down to the minimum number of states it has, and you take two DFAs and you apply this process to them, the idea is that you should be able to get two DFAs with the smallest number of possible states. In fact, it's even better than that. What you can do is you can take the two DFAs, and if you can manage to make one look like the other by swapping around any of their labels, as in their states, the states of their labels, as in the minimal DFA, because you'll end up with a much smaller DFA based on a concept where we check if two states yield a match. They do the exact same thing or they don't. But you end up with a minimum size DFA and you end up with two of them. What you could do is you could see if there's a way you could change around the labels of the states to make them so they look exactly the same. There's a couple other ideas around this. There's a thing called the table filling algorithm that is the part of the minimization process. But if you find yourself curious about this, I encourage you, if you feel like checking this out, you can check out the Hopcroft book. It's in Hopcroft. I think I call it HMU in the course outline. HMView. It's chapter 4.4. They have a very thorough explanation of how to do this. So if you're wondering why this is important, so think about it. So remember I showed you that I can take a regular expression. So imagine I have a regular expression. I told you that I can turn this into an epsilon NFA, right? And then I told you, okay, well, like I could take this epsilon NFA and turn it into a DFA. Now, do you remember, I want you to remember a little while back when I did this, when I made that construction had a lot of epsilon transitions, right? And a lot of states. So does everybody remember that? Where when I used that construction to get a epsilon NFA, and you know how I was building up those pieces, and they ended up getting quite big, right? It was a lot of states, a lot of epsilon moves and things like that. What it would be nice is if I convert this to a DFA after the modified subset construction, if I can minimize it. So the idea is that if I can minimize the DFA, then you end up with a minimum state DFA. So if I have a DFA with the smallest possible number of states, that's something that's a little bit more practical, right? So if you find yourself, hey, look, I want to know how you can make it so the DFA has way less states. There is a way you can do that. So I just wanted to make sure that you're aware of this fact. Is everybody okay with that? So if you find yourself curious about it, I recommend checking this part out in the Hopcroft book. It's kind of neat. I know that there's a very brief part in the Zipser book that does actually address this. I have it in the course outline where it is, if you find yourself curious about that. But yeah, no, that's all I really have to say about properties of regular languages. Are there any questions before I proceed? Are we all good? Give me a thumbs up if we're all good. Awesome. Awesome. Okay, good. Okay, now we're going to be switching gears to something that's going to blow your mind. I keep saying that, and I'm hoping that I'll get you a little bit excited about something that is a little bit more abstract. And I will admit, this is a bit more abstract than what I'm going to do next, but I'm hoping I can entice you with a general game plan for how we're going to go about this. So the question I really want to think about now at this stage is the following one. So up to this point in this class, we've talked about DFAs, NFAs, epsilon NFAs. We also talked about regular expressions. I told you up to this point that all of these are ways to describe regular languages. I can use regular languages to describe these. So they're one and the same. The ultimate question I have for you for today, and this is what I'm going to be addressing for the remainder of this lecture, is if there exist languages that are not regular. So that is the ultimate question of the day, is do they exist? Are there languages that are not regular? And I'm going to be addressing this and trying to convince you that the answer is yes, that there do exist languages that are not regular. So I'm going to be giving you a tool of sorts to determine if a language is in fact regular or not. So just want to give you just a general heads up of what we're going to do. To show a language is not regular, we'll use a theorem called the pumping lemma. So this is going to be one of those things that I'm going to make sure you have to know. So this is not something I should downplay. So this is the pumping lemma, and this is for regular languages. Because there's different versions of pumping lemmas. This is the one for regular languages. So it's called the pumping lemma. We will use a theorem called the pumping lemma. Prove via contradiction that a language is not regular. A language, okay, that's really terrible. I'm crossing it out. That's how boss I am being today on a whiteboard. That a language is not regular. So we're going to use this thing called the pumping lemma. So I have to first describe the pumping lemma to you. And I really want you to remember back to say something like your discrete mathematics background. Oh, this marker's a little dead. Bye-bye. It's gone. Okay, so what I'm going to be doing now is I'm going to describe to you this pumping lemma. And we're going to prove the pumping lemma is true. Now, before I do this, I must stress two things for you. First, this pumping lemma is a property of a regular language. So you can't use the pumping lemma. So the pumping lemma's job is not to test if something, like if I want to prove a language is regular, the pumping lemma is not for this. What it is that I can use, so if I give you a regular language, it must be that it satisfies this pumping lemma. So just to be clear, this isn't like a condition for knowing if it's regular. It's that if it's regular, it follows the pumping lemma. So naturally, if you think about things logically here, I'm going to use the contrapositive. So if I tell you that something, so if I say if a language is regular, then it satisfies the pumping lemma. If you take the contrapositive of this, recall that means that I just simply negate both of them and then I could flip them on their conditional. So that would mean that if the language does not satisfy the conditions of the pumping lemma, then it's not regular. That's the strategy I'm going to use. So watch this. So here's the pumping lemma. So this is the pumping lemma. And I really want you to pay close attention to the quantifiers that I use here. This is what commonly catches students when they're doing stuff with the pumping lemma. So I'm going to say, let L be a regular language. So I'm going to let L be a regular language. Now watch this. Now you have to be very careful with this. So I need you to remember about the quantifiers of existential quantifiers and universal quantifiers. I need you to pay very close attention to these because they're going to make a very big difference of how we're going to use this pumping lemma. So there exists constant P. And now, if you're wondering, this P depends, so I'm just going to mention this off to the side in parentheses. So it depends on L. So this depends on L and is called the pumping length. So whenever you see P like this, I'm going to refer to it as the pumping length. But remember, it doesn't have to be called P. It's just that you have to keep in mind this thing called the pumping length when we use the pumping lemma. Everything's about pumping. It's like pumping up balloons or something. I'll explain what the pump in pumping lemma means once I get through the statement here. So, such that, so I have there exists constant p such that for all, so notice I just swapped the quantifier here, for all strings W in the language with where its length is at least p, string W can be written in the following way: x, y, z. So string W equals x, y, z. That is, W can be dissected into 3 substrings, x, y, and z. This exists where, like I said, this first is going to look a little strange. Now I lost my penguin, but that's okay. I will save him later. Do need to give my penguin a name some point. So there's going to be these conditions on this W. So first, y is not equal to the empty string. The second condition is that the length of the substring xy, so if I take x and y, this can be no longer than the pumping length. And 3, for every integer k greater than or equal to 0, the string x, y, where I'm going to raise it to the exponent k, z is going to be in the language. So just to reiterate, just because this is very important that I do this carefully with you, there exists constant p, this is the pumping length, such that for all strings W in that language, with at least the pumping length, string W can be decomposed or divided into 3 pieces, x, y, and z, like this, where these 3 properties are going to hold. That y is not empty, that the length of xy is at most the pumping length, and for every k, if I take the y part and I raise that to some power k, remember that just simply means I can repeat y 0 or more times because k is 0 or more. So just as an example, note that if k was 0, this would be like me writing x epsilon z or just xz. So you might ask, Dan, what is this about? So if you have a regular language, here's the intuition behind it. So here's the idea. For any string W in the language with where string is at least the pumping length, there is always a non-empty string y near the beginning of W that can be pumped. So that can be pumped. That is, one can repeat y 0 or more times. And the resulting string is in L. So this is a property that every regular language actually has, is that if I give you any string in it and it's long enough, as it's at least this pumping length or this constant p, then there's always some way, there's always going to be this y here, the middle piece here, that's going to be non-empty, and it'll be somewhere near the beginning of w, within this first p symbols. And the idea is that it can be pumped. So when I say pumped, notice that this final condition here, what it says. So I have x, y to the k, z. So notice here that this y part here, I could put 0 there, I could put 1 there, I could put 2 there, I could put 3 there. I could do it as many times as I like. So that's what it means by pumped. So we're going to see what I mean by this when we get to the proof. And I'm hoping that I should be able to draw on a connection for you between something that I actually proved a couple lectures back and to this pumping lemma. Yes. So that's what you got to think about this y as. It's like a loop. But so actually, I want to make one more remark about this, seeing as you brought this up. So one thing about DFAs and NFAs and epsilon NFAs was that, of course, we have finite memory, right? Like we have only a finite number of states. We don't really have the way we used memory in quotation marks was we kept track of some state, right? But how did we make, like, I want to just first think about the NFAs first. So in an NFA, I had like a loop that allowed me to produce more guesses, right? That was the intuition that I used very often when I talked about an NFA. Now in a DFA, and this is something I would encourage you to try doing yourself when you have some spare time, is take an NFA, convert it to a DFA using the subset constructor into the lazy version. I'd recommend the lazy one, if you could. And see what happens with that loop. What happens with the loop that you use to produce more guesses? Like when we were trying to detect key phrases and stuff. Like what happens in the DFA, what it looks like. And it's basically what you'd suggested, is that there's some way that I can basically come back to where I started in the string when the length of the string is long enough. So it will correspond to something like a loop or a cycle. So that's actually what's going to pop up in this proof. That's an excellent question and a great point to bring up. So is everybody okay so far? So I'm going to prove this pumping lemma. So remember, this is a property that every regular language has. So I'm going to come back to this pumping lemma depending on how much time we have after we finish proving this. And I'm hoping I should be able to give you a strategy for how we're going to do this. And then we're going to do next time a bunch of examples of proving languages are not regular. Okay, so now we got to prove this sucker. Now at first this looks really complicated. This theorem looks very complicated at first. But believe it or not, the proof for it is actually we're going to find a very clever way that we can take together some discrete mathematics with the way we describe a DFA. And when we can put these two things together, the proof actually comes out quite nicely. It's actually kind of surprising. I know when the first time I seen this proof, it was a little like how did you prove that so easily? There's so many quantifiers there. You can see that like there's exists, such that, for all. And then there's another existential quantifier in there too. Like, it looks like a bit of a nightmare if you think about it, but it's actually not too bad if you think about it in a very specific way. I'll hopefully have time to talk about after this, if not next time. So I'm going to suppose L is regular. I'm going to suppose L is regular. Then by the definition, then by definition, there is a DFA. There is a DFA M where L of M, so the language that the machine recognizes, is equal to L. So now I'm going to describe where this pumping constant's going to come from, or the pumping length. So suppose M has P states. And let delta be the transition function be the transition function. Be the transition function of M. And Q0 be the start state. So far we should all be fine. This is just me invoking what regular means. So I want to make sure I give you an idea what I'm going to do with this. Is I'm going to give names to states as I were to process them given some string. Any string that belongs to this language. So I'm going to give you a sequence of labels I'm going to give the states of this DFA. And I'm going to try to prove something about these labels that I'm going to assign to the states. So I want you to pay close attention to how I do this, because this is the kind of the crux of the proof. So consider a string. Consider a string W, where W, the length of W, this is the length of W, is at least P, such that A1, A2, all the way up to AM, with M greater or equal to P, with M greater than or equal to P, like this. Because I might have a bunch of symbols I'm going to read. I just want to give M a name, so the number of symbols I am using when I process this. So, and every AI, so each one of the A's I have here is an input symbol. So now this is the part that I don't want to lose you. So now this is where I'm going to define names for states that are in the DFA. Now watch this. For each I equal 0, 1, 2, all the way up to P, define PI to be the following. Now, don't just give me one moment to write it, and then I'll explain what I'm going to do with this. Okay, so I'm going to have the extended transition function of, so given Q0, and then as I read A1, A2, all the way up to AI. To be particular, just to make sure I'm clear with everybody, this I'm saying i.e. PI is the state M is in after reading the first I symbols of W. And P0 is going to be equal to Q0. So what I'm going to do here is I'm using the extended transition function to give names to the states that are in the original DFA. So I'm going to call them P1, P0, P1, P2, all the way up to all the way up over here. So imagine I have all of these. Now, I must warn that I have P as the pumping constant or pumping length. So technically, I could rephrase this. Instead of using P, I could use a different symbol if you are really nitpicky about this. I kind of am. So now I'm a little unsettled about this fact. So, but don't worry. When I say, I don't even want to say it, okay? So what's going to happen is each one of my PIs are going to be the state that I get after I read the first I symbols. That's what this represents. So remember, that's the extended transition function for the DFA, which has exactly one state you'll give you. So don't let this thing look intimidating. Just remember, that's what it's all about. I'm just reading the first I symbols, and the state that I sit in is what is going to be called PI. Okay. So now this is where my little bit of discrete mathematics is going to be very helpful here. Notice that there cannot be p plus 1 distinct pi's as there are only p states. As there are only p states. Does everybody see that? So remember, the way I have this is that the DFA is defined so it has p states. And if I read more, say if I read more than p symbols, p or more, notice that there cannot be more than p plus 1 distinct pi's that I get as a result of this labeling process, because there's only p of them. And there's a name that we have for this in combinatorics, the counting rules. It's a lovely, lovely, lovely property that is unbelievably powerful in the way that you could use it in certain settings. This is one of those examples where it pops up. It's the pigeonhole principle. So here's how it goes. That is, by the pigeonhole principle, there exists two integers I and j, so that we have the following, so that this following part holds. So that 0 is less than or equal to I, is strictly less than j, but this is at most p. And now this is the part, remember, just don't read these literally like there are indexing. And remember, these represent, each one of these pi's represents the number of symbols you've been processing. And pi states pi is equal to pj. So if you don't recall the pigeonhole principle, imagine I have n discrete objects and I tell you I have to fit n plus 1 into those. That means that there's at least one of those objects that has to go into the same box. So you can think of it as bins. If I have like more than n objects and I have only n things to put them in, one of them's going to have to, there's going to be one that has at least 2. That's all I'm saying. It's a powerfully simple idea. So this is what this is saying, that there has to exist I and j such that the pi is going to be equal to the pj. And now I want to draw you a picture. So the question I have is it okay if I erase the top part of this? Are we okay with that? Because I mostly just want to make sure that we have this picture that I can draw for you. Okay, so I think we're okay. So let me just, where's my eraser? Oh, it's way over there. I want to draw you this fun picture. And this is exactly the one that was actually suggested a little earlier. So I'm just going to I'll leave this bottom part here. So I'm going to draw you a picture based on what I said here and how I defined each one of these PIs. So here's the picture. This should hopefully help you see where the Y and the X and the Z are. So remember I told you that P0 is in fact Q0. And there's going to be a bunch of stuff that happens in here. It's going to get me to some state Pi. And then, as I suggested down here, there's going to be some J, for which when I reach through those J symbols, it's going to effectively come all the way around like this. And then, if the string is in fact accepted by the language, is going to get to some final state. Now let me label these pieces for you, because these are the three pieces, the ones that I alluded to in the theorem. So this is X, this first part here, all of the transitions that are represented by the label of the path that gets me right here for that given string W is this. So A1, A2, all the way up to AI. So that gets me to PI. Remember, that's how I define this. Then I told you that because of the pigeonhole principle, I and J have to in fact be equal to not each other when it comes to the states, though they sit at different indices. Because remember, I'm just mapping over the DFA states, right? That's something I really want to stress. So what's this? Well, this is just Y right here. This is AI plus 1. AI plus 2, all the way up to AJ. So if I read all the way up to AJ, remember AJ, when I read the J symbol, sorry, the J, it's technically the J plus 1. Actually, no, it's a J. Well, let's go with the J. Yeah, it's the J, sorry. If I read that many, I get back to PI, which equals PJ, right? And then I read the remainder of it, which is Z. AJ plus 1. AJ plus 2, all the way up to AM. So there's our three pieces. There's X, Y, and Z. Then we can divide Y is equal to X, Y, Z. So I'm just going to summarize what I just said up here. X is going to be equal to A1, A2, all the way up to AI. So X makes us reach PI, but I must stress, because of the nature for which I process this, I must stress that notice that these indices, I and J, they both land on the exact same state. So one thing I need to stress is that X can be empty. Now next, Y, of course, Y is going to be equal to, Y is equal to the second part. That's AI plus 1, AI plus 2, all the way up to AJ. So this Y will take me from PI back to PI, which equals PJ, right? And I must stress that Y is not empty. I must stress that. That's very important. And of course, Z is everything else. And I must stress that Z may be empty. Now, if you're having a hard time seeing why this is the case, think about it. The machine has at least one state, right? Like P can be, like P is greater or equal to 1, right? Like, so this constant has to be positive. So you know that this thing's going to have to at least read some symbol. Assuming, of course, that this thing... Well, I'm not going to get too much into the details. I think this is enough to talk about. So I'll just leave it at this. Now, I'm just going to summarize the last part for you. The rest of this is more carefully written in the proof. So consider when M processes string x, y to the k, z for any k greater or equal to 0. Well, what you do is you break this into two cases. You have one case for k is equal to 0. And then you have a case for k is greater or equal to 0. Sorry, greater than 0. So if you think about it, just look at my picture I have up there. If k is equal to 0, what happens? If k is equal to 0, notice that I'm just going to get me right here. It'll get me right here. And then it says, okay, well, if it doesn't happen at all, like this doesn't go around, I'm not pumping the string. That means I go right from there to there. And that takes me to an accepting state, right? So this goes from, this is xz, right? And I'll say which it accepts. Like I said, I've written a little bit more carefully in the notes. And otherwise, you have your other case. This is where you have x, y to the k, z, which it accepts by very similar reasoning. It's because, look, I go from x, if I read all of these symbols, it takes me to pi. And every time I read a successive y, it takes me back to pi because pi is equal to pj. So what happens? Then I can get over here. I get to the final state. So these are your two possible cases that can happen. And that's effectively the rest of this proof, at least the general idea. Like I said, if you want a more careful explanation of these two cases, I have it in the notes. So are we okay if I get 1 or 2 more minutes from you? I want to give you a little teaser for next time. Or would you rather we finish today? Because I could always talk about it more next time. Just want to find out, just because I always like to ask for more time if we need it. Okay, finish? Okay, I'll finish right here then. So when we come back next time, I'll show you how we can use the pumping lemma as we proved it, how we can use that to show that there is a way we could show a language isn't regular. So that being said, I want to say thank you very much and have a good weekend, everybody. I'll see you later.